Hey everyone, today I'm just going to show you some proof of the second derivative test for inflection, okay? Or actually the second derivative test to prove that something is a minimum or a maximum, at least at that regional, during that interval. Okay, so let's just say that you have a point C. And in this point C, you got a graph like this. Let's talk about the minimum first, okay? And you got a point C in here. At this point C, just wonder something here, okay? At this point C, the first derivative is 0, okay? So f prime of C equals 0. All right. What about the second derivative? Let's go to the definition of what a derivative is. If you have f of x, okay, the derivative of this, dfx with respect to dx equals what? Equals the limit as delta x approaches 0, okay, of f of x plus delta x minus f of x divided by delta x. That's one way to think of it, okay? Now, if you have a point C and you want to check the derivative around this point C, you can also say, for example, that df at the point C with respect to dx, okay? Because this is still f of x, except that x is equal to c now. It's going to be the limit of f of x, an arbitrary value of x that's not c, okay, minus f of c divided by x minus c as x approaches c. You can see that this is the same thing as delta x. Okay, this thing here is the same thing as delta x. As x approaches c, delta x approaches 0. Okay, because what is in this case here? What is delta x? You got c plus delta x equals x. Okay, delta x could be positive or negative. If it's positive, x is greater than c. If delta x is negative, x is less than c. Okay, now this is the first derivative. If you want the second derivative, you got to check the derivative of the first derivative. So let's say we're checking the derivative of the f of prime c. So you got to do this and you got to do that. That's it. Okay, so I'm going to keep this thing here. I'm going to put it here as a reminder. This one here I'm going to erase. And I'm going to separate this here. You got this. Okay, you got this. And now we're dealing with this situation here. Now we have an interval that contains C. That means that it has to start somewhere around here and it has to stop in here. Okay, it's got to start before C and it has to contain C and end after C. Okay. Now, all right, what is the second derivative around this point C? It's going to be this formula here. All right. Okay, so let's check this formula. Like this. Yeah, I'm going to copy this and put it here. Okay, you got to remember for this point C here to be a minimum, okay, f of C, the first derivative with respect to x at the point C has to be 0, and the second derivative is got to be greater than 0. Actually, I'm sorry. Yeah, it's got to be greater than 0. Yeah, if it's a minimum, because it's the opposite. If it's a minimum, it's got to be greater than 0. If it's a maximum, it has to be less than 0. Okay, now this is the second derivative. This is the second derivative right here. And we're saying that this has to be greater than 0. Now, what is f prime of c? Well, we just noticed that f prime of c equals 0. So you can't forget about this. Okay, this is 0. So for this to be greater than 0, now look at that. If x is greater than c, this is positive. If this is positive, for this thing to be greater than 0, that means that this has to be positive. Okay? So when is this positive? To the right of c. So to the right of c, the tangent has to be positive, and the tangent is positive. Look, the tangent's just growing. Okay? Now let's just say that x is less than c. If x is less than c, x is over here, okay? Then x minus c is going to be a negative number. If it's a negative number, for this whole fraction to be positive, because it has to be greater than 0, okay? Then this thing here has to be negative. So over here, look at that. The tangent is negative here, and the tangent is positive here. So this proves this part here, okay? Now let's just say that you want to prove the opposite. You have this. I'm going to do it bigger. And this is the point C, where the tangent is 0. Okay. Now let's go back to this formula here again. I'm just going to erase this mess in here, and I'm going to put so here we have again the second derivative, okay, with respect to x and around the point C. Now, what is f of c? F prime of c, this is 0, okay, so this is going to go to 0, doesn't matter. Oh yeah, and now I want to talk about the second case. I want to talk about when this is less than 0. Because what does it say? It says that this here is a minimum. Now when f prime of c is equal to 0 and f double prime of c is equal to less than 0, this is a maximum. We got to prove this, okay? This video is just about proving the second derivative test to find out if the place, that point C, is a regional minimum or a maximum. So let's see here. F prime of C is 0, okay? And f double prime of C has to be less than 0. Okay, so this thing here has to be less than 0. This whole fraction has to be less than 0. That's great. How do we do that? If x is after c, x is over here, okay, then this is going to be positive. This is positive. For this thing here, the whole fraction to be less than 0, then this thing here has to be negative. Okay, so if x is over here, x minus c is positive, and the first derivative of the function has to be negative for the whole thing to be negative, right? Because you got a negative divided by a positive, this is going to be a negative, which is less than 0. Okay, so x is less than c, then the first derivative has to be negative. Look at this. The first derivative is negative. Okay, look at all these tangents. They're all going down. All right? Now, if x is less than c, then this is going to be negative. It's going to be around here. If this part down here is negative, the top part has to be positive. And look at that. The first tangent is positive. All those tangents, they're all positive. Look at that. Okay, so this proves this second derivative test. It's called a second derivative test. Okay, it proves that it can be used to find a regional minimum and a maximum around the point C.